Hello again, welcome to Basics of Finite Element Analysis. Today is the fourth lecture of this week, and in the last lecture we had discussed convergence, the notion of convergence, and we had also mentioned that FEA in general, not invariably but especially for conservative problems, in general it tends to under predict displacement, over predict systemic energy and over predict stiffness. So today and probably in next lecture we are going to expand on this a little bit in detail, and that is going to be the theme for today's lecture. So this is essentially a continuation of last week lectures, which is accuracy of solution. Okay. So before we start discussing this in detail, let us look at this equation, minus d over dx a du over dx is equal to q, and this equation is valid for the domain x ranging between 0 and L. I want to make sure that you understand, we have discussed this earlier also, that the governing differential equation always valid in the domain, it is not valid on the boundaries. Okay. The conditions at the boundary are defined by the boundary conditions. So it is important to understand that. Now this is a general second order differential equation. So this is second order ODE. And earlier we had said that 2m represents the order of the equation. So here m equals 1. Okay. 2m represents its order is 2, so m equals 1. Now this second order equation, it represents a very large range of phenomena. So we will like to give you a flavor of different phenomena. So for instance, we look at cable. So you have a cable and some weight is hanging on it and it is trying to bend. So for a cable, U represents transverse displacement. U represents transverse displacement, and A represents tension in the cable. Okay. And Q represents distributed transverse load. Okay. And finally Q naught, and what is Q naught? I will define that here. Q naught equals A times U prime at, let us say, x is equal to L or x is equal to 0. So or x is equal to 0. So Q naught is axial force. So the second order equation can describe the behavior of a cable under tension if I consider U as transverse displacement, A as tension, Q as distributed transverse load, and Q naught as axial force. This also represents displacement in a bar under axial tension, and here U represents axial displacement. And A represents Young's modulus times cross sectional area at position x. Q represents frictional load and Q naught represents axial force. So, this is case 1, this is case 2. Case 3, we will talk about heat transfer. Heat transfer. And heat transfer in a cylindrical pipe. So, it is a one dimensional system, cylindrical pipe or things like that. So, here U represents temperature, and then this A represents conductivity. Q represents heat generated. And Q naught represents heat. Similarly, the same equation also represents flow of water in a pipe, flow of water in a cylindrical pipe, okay. And I can again map out different aspects of the problem here. Another thing is flow in porous media. And then it also, the same equation also governs the behavior of for some electrostatic problem. So, the reason I am talking about all these situations is, and I can fill up all these things, but I do not want to spend any more time on this chart. But the reason I wanted to show you this chart is that this second order differential equation, where m corresponds to value 1, it is not just about one single physical problem, it can capture the reality of a very large number of physical problems, okay. And in this case the order of differential equation is 2, it is not 1 or 3, it is 2. Similarly, you have a fourth order differential equation. You have a fourth order differential equation. An example of this could be d2 over dx square ei d2w over dx square is equal to f x. This is the governing equation for a Euler-Bernoulli beam, okay. It is for an Euler-Bernoulli beam. Here this is a fourth order and m is equal to 2. Okay. And make sure that here I have a negative sign and here I have a positive sign. So, I have a second order differential equation and I have a fourth order differential equation. So, but I do not have a third order differential equation because I am not aware of a physical process or system which can be represented by a third order differential equation. So, in general, such types of equations can be represented in this form: I equal 1 to m minus 1 to the power of I Ti over dxi Ai diu over dxi equals f. Okay. So, this is a generic form of differential equation which captures both fourth order and second order, right. It captures both fourth order and second order. So, here x varies between 0 and L, right, and AI is actually a function of x. AI is a function of x and u is the exact solution. U is the exact solution. If I have an FE solution, then I will call it UH. Now, we will do an example. Let us say that m is equal to 2. So, if m is equal to 2, then this whole equation will have left hand side will have how many parts? It will have 2 parts, right. So, when m is equal to 2, then this m becomes, m is equal to 2, then my first term is minus 1 to the power of 1 d over dx a1 du over dx. This is the first term, right, plus minus 1 to the power of 2 d2 over dx square a2 d2u over dx square is equal to f. Okay. F can also be a function of x. Okay. Now, if a1 equals 0, then I get a equation for beam. Euler-Bernoulli beam. If A2 is equal to 0, then I get equation for bar or heat conduction, so many other problems which we discussed in this table, right. If A1 is 0, then this term goes away. If A2 is 0, then this term goes away. And also note that I have minus 1 to the power of 1. So, sign is also taken care of in this format. So, to discuss this accuracy and this convergence process, so what we will do here is we will discuss this problem, this feature of finite element in detail, that why does it converge from bottom or top and so on and so forth. So, in our subsequent discussion, we will assume that A2 equals 0. So, we will try to understand this concept of convergence in context of the bar problem, and we will also assume that u is 0 at x is equal to 0 and u at x is equal to L is also 0. So, if that is the case for these boundary conditions and for this condition, the overall governing equation. So, first what we will do is, so initially we will be more general and later on we will implement these conditions. So, we will start from this equation, or this can be abbreviated as this equation. We will develop this equation further and later we will set m as 1 and so on and so forth. Okay. So, we will start from this equation. So, this is the overall governing equation for a large number of physical processes, and for this equation we will develop a form called a variational form. So, let us call this equation A. So, we will develop variational form of equation A, that we will discuss now. So, how do we develop its variational form? In FEA1 we have discussed this, but to recap, what we do is we will multiply this equation A with a variation, right, with a variation, a small perturbation, and let us call that variation V. So, we will multiply this by V, and we will integrate it over the whole domain, and we will not only do that, we will also see here the differentiability is on u is either of second order or of fourth order. So, we will weaken the differentiability and shift some differentiability to v. So, that is what we will do. So, the variational form of A how do we get it? Multiply A by variation V, then weaken differentiability, and then we will also get some boundary terms, right. So, what we get finally is 0 equals weaken differentiability and integrate, weaken differentiability by integrating by parts. So, this is what we get. So, once we multiply it by V and integrate it by parts, this is a weakened form, and once we are integrating it by parts, we will also get some boundary terms. Right, we will get some boundary terms also, and we assume that the nature of the problem is such that all these boundary terms are 0. You can assume that. So, for instance, if I have a bar, I can assume that displacement at one end and displacement at the other end is 0, or at one end displacement is 0 and at the other end force is 0. So, it is a free end. So, in the boundary parts we have displacement times force term. So, if one of them is 0, then 0, right. So, boundary term is 0. So, this is the variational form. So, this is, let us number this equation as equation B. Now, we develop a quadratic functional. You develop a quadratic functional for B. Now, to understand what is quadratic functional, I will suggest you go back and look at FEA1 lectures. But what we will do is, in this lecture also we will explain a little bit of how we develop this quadratic functional. Okay. So, corresponding to, so for B we develop a quadratic functional. So, here we develop this when m is equal to 1. If we swallow the same procedure, we can also develop it for 2, but here we are going to develop it when m is equal to 1. Okay? When m is equal to 1, this is what we are going to develop it. So, when m is equal to 1, equation B becomes 0 A1 du over dx dv over dx minus Vf dx, right. So, let us call this C. Now I will first write an expression, and then we will see that that expression is indeed related to this equation C. So I will write this expression, and this is a quadratic functional I, it is a functional of u, is nothing but 0 to L half, for sake of simplicity I will remove this subscript 1, okay, I will remove this subscript 1. So a u prime whole square minus u f dx. We will see that this I, this is a quadratic functional, this I is related to equation C. We will see the relationship just now. We will develop that relationship. So what we will do is, for this relation, we will find its variation. And how do you find the variation? You replace u by u plus epsilon v, where epsilon is a very small number. It could be 10 to the power of minus 50, extremely small number, as small as what you can think. So very small number. So once I replace u by epsilon v, what does this mean? What I am doing is that this is this expression, and I am replacing u by u plus some very small disturbance in u, okay, very small disturbance in u. So then I will see how this I gets disturbed. I am finding out the disturbance in I when u gets disturbed by an extremely small amount, which is of v. So this is equal to 0 to L half a u plus epsilon v, and this is epsilon u prime. Epsilon is a constant, so its derivative is 0. So I have u plus epsilon v prime minus u plus epsilon v prime. Okay. So now I expand it, 0 to L half, there is a square term here, right. So half u prime square plus 2 epsilon u prime v prime plus v prime square minus u plus epsilon v prime f dx. So this is actually not u plus epsilon v prime, but u plus epsilon v. So now I reorganize all this stuff, and I take terms half a u prime square minus u f dx, this is one portion, plus 0 to L a epsilon u prime v prime, excuse me, I have to rewrite again. So epsilon times a u prime v prime minus v f dx plus a third term 0 to L epsilon square. There is one thing, this is epsilon square is also going to be here. right, epsilon square. So, epsilon square v prime square dx. So, what I have organized this entire expression, broken this entire expression into part 1, part 2, part 3. In the first part there is no epsilon, in the second part there is epsilon with the power of 1, in the third part there is epsilon with the power of 2. Okay. Now, we will see what all this means. Okay. So, first thing we remember is that equation C. How did we get this equation C? This equation C came from the differential equation, and then we multiplied it and then found its variation. So, this represents the right. So, this represents equilibrium, because the ordinary differential equation was the differential equation for equilibrium, and equation C has directly come from that equilibrium situation, right. So, this represents equilibrium of the, if it is a bar then it is equilibrium of the bar, right. Now we will look at this term. This term is what? A. So, if there is a bar under tension, then A is equal to E times A, right. A is equal to E times A. U prime is strain energy. So, strain times U prime is stress, and so it is stress times strain, and when you have a stress strain graph, right. So, it is stress times area. So, it is force. So, right. So, it is x, no excuse me, epsilon and stress. So, the area under the curve is strain energy. So, E, see, A is equal to E times A. A times strain is stress. A times strain, no, I am sorry, E times strain is stress, this thing. So, what I am multiplying is stress times strain, and half of that is the strain energy density, right. And when I multiply it by area times dx, it is the strain energy, because I am multiplying it by volume. So, this represents strain energy in the system, right. This represents strain energy. This represents strain energy. And what does UF represent? U is displacement and F is force. So, this is external work, right. So, this is the total work done in the system, right. Strain energy internal work, and this is the external work. And our principle of minimum potential energy says that whenever the system will be in equilibrium when the potential energy of the system is at a minima, right. So, this I represents the overall energy, potential energy of the system, and what I am doing is I am finding its variation. When I replace U by U plus a small variation, then this is the basic potential energy, this is the first variation because it is multiplied by epsilon, and this is the second variation in the energy, right. This is, so this is first variation, this is second variation, this is the second variation, and whenever a function or a functional has to be at minima, what is the condition for that? That its variation or its first derivative, for a function to be at a minima, the condition is that its derivative has to be 0, derivative has to be 0, first derivative has to be 0. Similarly, for a functional, so this is a functional, I is a functional, for functional to be at a minima, its first variation has to be 0. So, this first variation has to be 0 for equilibrium, right. For equilibrium, this first variation has to be minimum, which, and when you look at this, what are the terms here? So, since epsilon is constant, I can, since epsilon is constant, I can take this epsilon out. I can take this epsilon out because epsilon is a constant, it is a small number. And when first variation is 0, which means that this entire thing should be equal to 0. This equation is same as this equation. So, let us call this equation D. So, this equation is same as this equation. Okay. So, you see that this I is a functional, it is a quadratic functional because this I am having u prime square, and its first variation when it is equated to 0, I get equation C. So, this, so let us call this equation E. So, I can say that E is a quadratic functional of C. E is a quadratic functional of C, and in reality, at least in context of the bar problem, it represents the energy on the system. Okay. So, I can write that E is a quadratic functional of C. So, I will close this discussion here, and we will continue this discussion in the next class, and then we will show how all this understanding can lead to a conclusion that energy convergence in FEA solution happens from above. Okay. Thank you.